Hey, all you cool cats and kittens out there. It's Carol Baskin with the Big Cat Animal Rescue. Hello? Well, maybe you got that reference. Maybe you didn't. I hope everything's going well. A little in a vacuum here, knowing exactly what folks are doing. But I'm going to keep going because that's all I can do. And it's really up to you to be responsible for learning. I've got 3 more examples on what I'm calling disc and washer techniques for finding the volumes of solids formed by revolutions. So I'll work through those examples. And you've got that. As you have probably heard by now, we are reduced to 1 grade each week. And I have put together a Canvas quiz that is due Friday for you to do. It does not include revolutions. It is only over area between 2 curves, which we started last week, and volumes of solids of known cross sections. So this is the 3rd topic that we're continuing on in this unit, really an application of what we're doing with integrals. So this and yesterday's lesson is not on this week's quiz, and this week's quiz is due Friday at midnight. I know that Friday's a holiday. It's available now. You can do it. I am not closing out the availability on it, so you can do it over the weekend if you need to. I'd prefer you get your work done and have the weekend to relax and take a break. So that would be me. That's why it's available now. So let's do these examples. Remember what we've got, and yesterday I had visuals to try to help. What we're doing is revolving either around an x-axis or a y-axis, or in this case we're going to do some examples today about axes of revolutions that are not an x-axis or y-axis necessarily. But I'm going to have a couple. In fact, I'm going to use these examples. So let's title this page today, or this lesson, More Disc and Washer Examples. And I'm going to use this region or these functions for all 3 of these examples as we go through. I think that'll just simplify the types of problems that we've got. So when I refer to in these examples f of x, that's going to be the square root of x plus 1. So the square root function shifted up 1, and g of x equals x squared plus 1. The parabola shifted up 1. Okay? So let's do an example here. Example number 1. Find the volume of a solid generated by revolving. And that should be a key word that you're looking for, not necessarily generating. That's kind of a blah, blah, blah word. But generated by revolving, that's the word we're looking for. The graph of f and the line y equals 2. So that's our region. We've got the graph of f, square root of x plus 1, and the line y equals 2. I'm going to try to fix our focus here because it looks a little, let's see. How's that? Is that better? Looks better to me. So back to our, yep, we're still recording. So find the volume of a solid generated by revolving the graph of f and the line y equals 2 on this interval from 0 to 1 about the line y equals 2. Okay? So a little different. Let's sketch our graph here. We've got our axes. The square root curve is shifted up 1, so I'm just going to make this real quick there. Shifted up 1, something like that. And I know that it is bounded by the line y equals 2, about the line y equals 2. So there's our axis of revolution here. On the interval from 0 to 1, so that would make sense because square root of 1 plus 1 more is going to give us 2. That would get us up to line y equals 2. So that would be your intersection there. Okay, so this is the region that I'm not going to color it in nice and bold and obliterate because I'm coming in next to draw in my representative rectangle. If you understand what you're doing, drawing that representative rectangle will help you with the situation. There it is, okay? So I've got a rectangle all the way from 0 up to 1, and this time I'm revolving it around the line y equals 2. So that's why I drew that arrow there. Okay, so we're revolving it around that line right there. So we'll put a little curve to it right there. Okay? Now, some of you should be asking, is this disk, is this washer? Is there a hole in this solid? No. The rectangle touches the axis of revolution, so I know I'm not subtracting anything out. Okay? However, I need to figure out what my R is. Okay? And that's what I would spend time in. Well, if we were in class, I would have you all repeating after me, what is R? What is R? Just like what's the slope of the tangent line, the derivative, what's the area under the curve, the integral. What is R? In this case, since this is a dx kind of problem, we're going to find R, the height of that rectangle, which is what's being revolved around that line y equals 2. The height of that rectangle is really top minus bottom. Top minus bottom. So 2 minus the bottom of that is square root of x plus 1, and then I'm going to square that. Now, I agree that this square root curve is actually my outer surface, but since I'm going to square that, the SIGN sign will get washed out, so we don't have to worry about that. Okay? So top minus bottom is going to work, period. Okay, so just do it that way. So if I were to simplify that, R equals what? Well, if I distribute that minus 1, isn't this 1 minus the square root of x? And then I'm going to set up my volume. Volume equals pi, and again, just to remind yourself, volume equals here pi times the integral from a to b of r squared dx, let's say. Okay? Well, pi times the integral from, what are my limits of integration? They told us that, from 0 to 1. Okay? What is my r? I'm going to square that bad boy, so 1 minus square root of x squared dx. Now, you should have availability to technology. Okay, so either get some, find a friend, find an app on your phone, but you need to have technology because I would expect you to be able to do that. If I were typing this in my calculator, I'm going to not forget about it, but just kind of postpone the pi, do this integral from 0 to that of that. And clearly you'd want a calculator for this. I mean, I understand that these can get fun. And then throw in a pi after this. So if I just did this and math frac that bad boy, I'd get 1 over 6. But my answer is going to be pi over 6. Okay? So a lot of the challenge in these problems is setting up the problem. Don't worry so much about integrating this. And I don't know how they're going to test this because some people will have calculators. Some of the folks that they're worried about equity and all that fairness business may not have calculators, so they won't. I bet they will find all kinds of clever ways that the calculator really isn't going to give you much of an advantage. Okay, so you'd want to be able to do that. All right, pi over 6. Let's do another example. Same f and g. This time I'll use both of them. Find the volume of the solid when the region bounded by f and g on the interval 0 to 1. Whoops. Okay, that's a closed interval, sorry. Find the volume of the solid when the region bounded by f and g, so f and g, they're at the top of your notes there, is revolved. So there's our key word there. We've got a disk or a washer kind of problem, revolved about the line. Y equals -1. Okay, and just as a reminder, f equals square root of x plus 1. G is x squared plus 1. So I'm going to graph those real quick. Square root from 0 to 1 is going to look something like this. The x squared plus 1 is a parabola shifted up 1, but we're just going to be worried about that portion there, so it kind of looks like a petal. Okay, from 0 to 1, so this is our square root on the top. This is our x squared parabola on the bottom. And our axis of revolution is all the way down here. Y equals negative 1. Y equals negative 1. So here's my representative rectangle. But this down here is what I'm revolving it around. Y equals negative 1. So I've got F on the top, G on the bottom. You've got that. Okay, so let's figure out what R is first. R is my outside, my farthest away surface. So that's from the square root function all the way down to negative 1. Okay, so yeah, top minus bottom will prevail. Square root of x plus 1 minus my bottom is actually minus negative 1. So that equals what? Square root of x plus 2. Minus minus 1 plus 2. Little r is my inside surface. So it's this here. This is little r. Okay? There is definitely a hole here because I can see that my representative triangle here does not touch the axis of revolution. So I know I'm going to have to subtract out. Little r is what? Well, the top of the little r, right, because we're finding that length, is x squared plus 1 minus what? The bottom of my little r is minus negative 1. So that's equal to x squared plus 2. And remember, since we've got a disk application here where we're subtracting out, we've got pi times the integral from a to b of r squared minus little r squared. And this time it is a dx. Okay? Because again, my representative rectangle, I'm about the line. Your rectangle is always going to be perpendicular to your axis of revolution in these applications. All right, well, let's set up our problem. Volume equals pi integral from 0 to 1, big R squared. So I'm just going to write it in. Square root of x plus 2 squared minus little r squared, x squared plus 2, all of that squared. All that is a dx. And clearly I'm going to want a calculator for that. I think everybody would agree with that. So that's going to be equal to 49 pi over 30. So that's a lovely answer. Again, if you're going to go dirty decimal, I don't know what the dirty decimal equivalent is, but don't say 1.83 pi or something like that. It wouldn't be that, but it'd be about 1.5, I don't know, 1.56872 pi? No. If you're going dirty, go dirty all the way. Exact answers are always preferred. All right, so we saw an example where it's not the axis, but it was a disk method. It's not one of the axis, x-axis or y-axis, but it was still a disk. Here we're revolving it around a line y equals 1. Let's try another one. Example number 3. Find the volume. On a solid. When the region bounded by F and G on that same interval from 0 to 1. So I've got that same region, okay? Let's see what's revolved around. Is revolved about the line x equals 2. All right, so now we're finding the volume. So same region, let's sketch that in, but now I've got a vertical axis of revolution, so that's something I need to think about. We have something like this and something like this, right? There's our region there, okay? On the interval from 0 to 1, right? So this is still from 0 to 1, but so this stops here at 1. But this is the line x equals 2, isn't it? X equals 2. This is my axis of revolution, so it's a vertical axis. This is my f function on top. This is my g function on the bottom. But this time, my axis is going vertical, so my representative rectangle has to be horizontal. This is a dy problem. Immediately when you fix that, you set yourself up for making a dy problem. Okay? So instead, I need to find big R. Well, big R is my surface on the outside. That's still my f function, but I might need to think about that because remember, we said that f is equal to the square root of x plus 1. Okay? However, if it's a function of x and I've got a dy, so I might have to say y equals square root of x plus 1 and think about that. G we said it was what? X squared plus 1. So, in other words, y equals x squared plus 1. That's going to be my inside function, isn't it? There it is, little r. Okay? So if y equals x squared plus 1, I need to solve for that. So I'm going to subtract 1 from both sides and solve for x. Remember, this is an x value as a function of y. The x changes as a function of y. Why is that important? It needs to be a function of y because I've set up my problem to be rotating around a vertical axis. So this has to be perpendicular to that. That makes it a dy. We're going to accumulate on that. Just because it says from 0 to 1, we might need to change those limits of integration too, because that's not 0 for y, is it? Because it's clearly shifted up some. So lots of things to think about. So if I solve this one for x, I'd get square root of x equals y minus 1. X equals y minus 1 squared. Now I'm going to worry about the domain in just a second, but that would be your r there. Or not the r, but that's going to help us get r. Let's find our g function. So this is f, but now this is really our f idea, the outside curve. Solve this one, we get x squared equals y minus 1. And given our domain here, I'm going to solve for x. Isn't x just positive? We're not going to the left. So we've got square root of y minus 1. All right? So let's get our big R. Big R. Before it was top minus bottom. Now I want you to think right minus left, and that's how we're getting that. So the right side, the x value is 2. Minus my left is this one right here. Y minus 1 quantity squared. That's my big R. Little r is the inside surface, the closer to the axis of revolution. That's inside the surface there. So that's still going to be right minus left. 2 minus, well, this left curve of the g function here is, in terms of y, 2 minus square root of y minus 1. And we're still going to use our integral here, so pi. I'm going to come back to those limits of integration. I want to make sure that we get this set up right. This would be this term, 2 minus y minus 1 quantity squared, right? Minus little r squared, 2 minus square root of y minus 1, square that, and this is a dy. And what seemed like a very trivial matter before, this is our variable of integration, is now hopefully a big deal. So I'm hoping that this is sinking in, why this is something that we really need to be careful about. What are our limits of integration? They also need to be y values. So even though we said originally it was on that interval from 0 to 1, those were x's, right? So f and g were function of x's, those are x's. Well, when x is 0, what do those two intersect at? They intersect at the point y equals 1. When x is 1, right here, I would just plug it in. When x is 1, we'd get y is 2, or x is 1, we get y is 2. So we're doing the integral from 1 to 2 of that, and then we take care of all of those. How many of you want to expand all this out? Great. If you do, that's certainly an option that you could do. You could also use your calculator. Forget about the pi for just a moment. Math frac that, and you would get the answer 31/30ths. But I'm going to remember the pi. 31/30ths times pi is your answer. That's the volume of that one. Okay? So these are a little more advanced examples that should help you when you're not just revolving around the x-axis or the y-axis. And it's also good to practice a couple of the vertical axis of revolution where the problem is a dy. Okay, and you'll see those as well. All right, so quiz this week is over not this material. The quiz next week will be over this material, so you've got a chance to get some time to practice in, and I'll post some practice problems tomorrow. But today's lesson day, and I do have a quiz available for you, so you've got those as options too. So quiz is due Friday. Get it done sooner than later. Don't let it hang over the weekend. And that will be our daily grade for the week on that grading that quiz. And I'm sure all kinds of leniency and love will be shown as I type in grades into the grade book. Have a good one. Reach out if you need some help. If you know a friend who's not reaching out and needs some help, reach out to someone else to have them be helped. You know what I mean. And I hope everybody's having a great day. Email me if you're having any questions. Talk to you soon.